Okay, now we continue to talk about the relation. And in the previous sessions, we just discussing about what is the means or what is the concept about the relation and the relation some features or just how to compute the relation. And in fact, relation in computer world can be seen as a special set, especially just as the tuple set. That means the relation set, the element is a pair. That means they have just as their pair, just like this, their pair A and B. And in fact, it can be just seen as a subset of the two set the projection. That means set A times set B, and this just can be seen as each the subset can be seen as a relation set. And since it is as a set, so we can just using the set operation such as the union, intersection, and minus, and any other the set operation can cope with this relation set. And its result is also can be seen as a subset of the projection set. So it is also can be seen the relation. So we just say the combination relation. That means we just combine the two sets using the set with the set, the operation, union, intersection to just compose the relation set. So it means that we can just using the set operation to generate the new relation set or new relation. And we have mentioned this example, and now we just give you from the video, just more the example for this combine the relations. Okay.
So when we combine relations, we're essentially using the same rules that we do when we just combine any other set. So it doesn't matter that it's a relation. Just like I could find A union B, which would be all of the elements of A and all of the elements of B, I could do the same thing for R1 and R2. And so that's what we're going to do is work through these together. But all of these concepts should be familiar to you.
So here I should be careful. That means this is a set operation. For example, the union or intersection just depend on which is the set you want to union or intersection. If it's just the two union the set A and B, so you get the result maybe 1, 2, 3, 4, and 0. But we are just to union with the relation set. So relation set is come from the just the set A and B, but they're different from A and B. They're just the tuple set. That means here element is the tuple, the two part for pair, and from the A and the B. So it's the different union. Also, we are just using the set the operation union and intersection, but they are just their concrete set different, so their the unit results are also the different.
So we're going to start with R1 union R2, and that means this is the set of all ordered pairs that are in either R1 or R2. So 1, 0 is in R1, and then I'm kind of a geek, so I like to go in the right order here. So 1, 1 is in R1, but also in R2. And then 1, 2 is in R1, and then 2, 2, and 3, 2, and 4, 2. So it's every element that was in either R1 or R2. It's a union. Now the intersection, again, is only elements they have in common. So the only thing that they had in common was the 1, 1. 1, 1 is in both R1 and R2, and that's the only ordered pair that occurs in both relations.
So here are the set operation, the union and intersection, but they are just the parameter R1, R2, not A and B. So you will find R1, R2 also the set, but their set element is a special element. It is come from the set A and B, just have a pair. It means have two parts. The first part you come from A, and the second part come from B to compose the tuple of the pairs element or this relation set.
R1 minus R2, remember when we're doing subtraction here, the order obviously makes a huge difference. So for R1, it's all of these elements except anything that I can take out because it's also in R2. So really that's where this intersection is going to come into play. So because R2 contains 1, 1, I'm going to take it out of R1. So I'm saying 1, 0 is in R1, and it wasn't taken away by being in R2 as well. And then 1, 2 is in R1, but it wasn't in R2, so R2 didn't take it away. 1, 1 was in R2, and so R2 took that 1, 1 out of R1. And then lastly, I have, of course, 2, 2. And 2, 2 is in R1 minus R2, again, because it's not being taken away by any of the elements in R2. We're going to use that same logic going in reverse. So going in reverse, I'm starting with R2. And if it also is in R1, then it's not going to be in the difference of the two relations. So again, I can't use 1, 1 because 1, 1 is actually an element of R1. So, sorry, it's very writing it in there. So 1, 1 doesn't work. 3, 2 does work because 3, 2 isn't being taken away by elements of R1. And 4, 2 does work because 4, 2 isn't being taken away by elements of R1. the very last one we haven't used often. We did talk about this way back in our first unit of study when we talked about conjunctions and disjunctions and all of those things. This is the famous XOR, and XOR is the exclusive OR that says it's either in R1 or it's in R2, but it's not in both. So it's kind of like what we did here with the difference, except we're saying it's the union minus the intersection is really what we're looking at here. So essentially it's all of my values would come to zero from this union, except I have to take 1, 1 out of it. So 1, 1, I'm sorry, 1, 0, 1, 2, 2, 2, 3, 2, 4, 2. So again, XOR is in one or the other, but not both.
So just based on the set, the operation, you can to define many or new the different set operation, and using this just the new the set operation to do the computation for the set or for the relation set, and then to generate the new the relation. And for this XO, maybe we just discussing a little before. So you just to listen. If you didn't understand, don't care about that because you just seen as a set operator XO. That means it is just maybe or but not both. So XO. It is just similar as or, but it is cannot be both. Just so it can be compute just the union R1, union R2, and minus their intersection R1, intersection R2. It can be seen like this. Okay. So here just to show you about the more the concrete the example for the combine the relation. Okay. And for this the relation, then we can to just like this. We just from this we can just compose. We just before the concept we just say we can using the set operation to direct the combine the two set, just using the set operation to combine the two the relation set. And now here, we just give the concept. This concept is composition. And this composition, it is maybe we have also mentioned in the function or in the just the previous, we also to mention about this composite for just the relation or for the function. And now we just to discussing more about this concept. So the composition just to combine, but this is a combine the relation, the two relation, just using the different way, not as a set, just directly using the set the operation directly. And here just to define the composite. So the composite you can see maybe just from this the concrete this example. For example, here is the relation R, and we just using the map. This is a map to describe the relation R, just from A to B. So R is from A to B, and A to B, and we just can using this arrow to map or to just list all of the elements. That means, for example, here is this A, and to this, for example, this if B1, B2, and B3, then we can say this can be A, B2, C, B1, and B, B3, and D, B3. We have 1, 2, 3, 4. We have 4 arrows, and that means for R, this relation set, we have the 4 the pair element. And secondly, we just have the relation S. This relation S is just it is a map that means from B to C, map from B to C. So you will find it similar as a function, but in fact it's different as a function. We can know that function is the a special relation, and here we just the global map. It is just the map from B to C. That means this arrow and from B1 to Z and B2 W and B1 W and also B1 B2 to W. So for here we also have 1, 2, 3, 4, 4 the pair element for S. But now we just want to compose. That means the composite of the R and S should be careful. We just denoted or just writing down like this. And there's a small circle and between RS, but should be careful. We not write RS. We just write here. That means the composite of the relation R and S, we should be the for the first R, we write the right, because here we just using as the from the right to left, because we know that if we just from the function, maybe you can remember if we just say f and this compute function, maybe you can to understand. So we first to compute gx and is equal to gx and then fx. So it is just mean that the right first, if the writer and their first application, and similarly for this relation is the compose R and S. So we just write down S with R. Then that means just like this function. So it is similar for the compose function we have mentioned in the previous topic. That means we just using this circle, but here is the smaller circle, and here just to give you the composition of the relation. Okay, and maybe we just give you more this example from the video, just to show you about the relation, the composition. Okay, relation composition.
Mess up your solution. So those are our solutions for all of the combining relations practice. Those two functions back when we learned composition of functions. And in composition of functions, typically it was either written f of g of x in this format or f of g of x. And in either of those, the order in which we did any of our operations is we would first compute g of x in either situation, and then plug that value in to our function f. So I point that out only because the order that we're going to do this in will make a huge difference as well. So again, we're just going to be starting with the one furthest to the right and then moving left, just as we did with composition of functions. So a composition of relations happens when R1 is a relation from set A to set B, and R2 is a relation from set B to set C. So the key item here is this set B and this set B have to be the same set, because if they're not the same set, then your composition isn't going to work. And this will make sense when we go through our example together. But just know that the only way it's going to work is if that same set is being mapped to from R1 and then is doing the mapping in R2. So the composition will give us the ordered pairs A comma C such that AB was in R1 and BC was in R2. And again, notice the value of B has to be the same. So this will make a lot of sense once we actually go through this question. So let's go ahead and take a look. We are given R1 and R2. And again, notice this would be set B 1, 2, 3, 4. And then this would be set B 1, 2, 3, 4. So we're set because set B is the same as set B. And we are trying to compose R2 composed with R1. And again, keeping in mind, we're going to be starting with elements of R1. So here's how it works. We start with the first element of R1, and I'm just going to get rid of all of my markings here just to make things a little clearer. So we start with the first element of R1, 1, 1. What I'm going to do is I'm going to record, the first value of that ordered pair. But I'm not going to record the second value of the ordered pair because that's sort of my B. And so what I'm going to do is I'm going to find that value as the first element of an ordered pair in R2. So looking here, I found 1, 0. So 1 maps to 0, and so I'm going to record the 0 from R2. And now I'm going to move on to my second value. My second value is 1, comma 3. So again, I'm going to write down the 1 from R1, and then I'm going to look for the 3 over in R2. So in R2, I found a 3, and I found another 3. So I actually have two 3s. So what that tells me is I'm actually going to have two ordered pairs. The first one is 1, comma 1, and the second one is 1, comma 2. And those both occurred from this second ordered pair. Good. Now let's continue. I've got 1, comma 4. So 1, comma 4 means I record the 1, and now I'm looking for 4. 4 maps to 1. Well, if you'll notice, that would be the ordered pair 1, 1, which is great, but I don't need to write it down because it already occurred. So I'm going to get rid of 1, 1 because it's already in my set. Now let's take a look at 2, comma 3. So I'm going to write down the 2, but now I'm going to look for what 3 maps to. And 3, again, maps to both 1 and to 2. So I've got 2, comma 1, and I've got 2, comma 2, because I had to use both 1 and 2. And then my last one is, oh, sorry, I've got 2 of them. 2 left. I'm getting ahead of myself. I've got 3, comma 1, and again, that means I'm going to write down the 3, and then I'm going to look for 1, and 1 maps to 0. And then running out of colors, let's go back to white. I've got 3, which maps to 4. And again, now I'm going to look for 4. And 4 maps to 1. So that is my composition of R2 composed with R1.
So from this concrete example, we can to find their rules. That means if we just write down it is a composition result by hand, then you should be careful to first you should to select which the set relation set you want to begin. And here we just begin from R1. That means from the rightmost to select to begin, and then you should be careful because it is have the pair. So, and then from the composition, that means we just have a connect or just have can be seen as the bridge from these two pair, and then we can also to say the transition. Just for example, if just from this map, if just the compose, it can be seen. It's like from A to B2, and B2 can be reached the W and Y. So A can reach the W and Y. So if just to compose or just to describe as this map graph, then we can translate this just the composition, this task into just find the path. Because if you just for this the set, if you just by hand, then you will find where just to find where just find their certifying the definition. Maybe you just to check one by one and just using their whether or not they have same this pair. That means the first is the second part and the second pair just the first part, whether or not they are same. If they are same, we can connect just like this. But if we just using the graph to describe, then we just translate this. It can be to find from S element to reach, whether or not reach the C element, but we just to pass through the B element. So A can reach all the elements from C, then we can say A from this node can reach only can reach B2, and B2 can reach the two element or two nodes in C set. So A can reach W and Y just pass from B2. And similarly, B can reach the sixth element because B can reach the B3, but B3 no any error from B3. That means no any error from B3 to the C. It is just broke down. So although we came from B, here note, just we can begin from B, then we can reach this the middle layer, but it is the end. We have no any path to reach the C element. So B cannot reach or have no way to reach the C's element. So B have no way. And C is okay. C can reach the B1 and B1 can reach W and Z. So here that means we can write down, for example, this result. It is means that the first A we have mentioned that A can reach the W. So A, W, and here A can reach the Y. Okay, can reach this. And here, if from B, there are no way. If from C, then we can from B1 and B1 can reach the W and Z. So we can say CW and CZ. Okay. And continuing from D, if we just reach from D, we can reach the B3, but similarly, no way to reach. So finally, we only have the four arrows from A to C. Four arrows from A to C. Just using this middle, we can say the middle layer or middle node. So finally, without this compose R and S, should be careful. This R in the right, not left. Okay, so that means if we just give you this map, we also can compute its composition result. And if just give you this the set, just the similar we have from the from the video, we can just from you can use the definition from this combination, the definition to define one by one. And also you just describe this the graph, then we can just find the path. And the later we will just if we just use the matrix, because in the previous sessions we have mentioned we have three ways to describe. We have three ways to describe this relation set. First, just from the set, the original definition, list all the set elements, or sometimes you can, if you just have more, you can just write down just the rules, the set rules. It is similarly using the set description. Okay, And the second way we can use the graph, just like this arrow graph, the diagram, okay. And also the last chapter we just talk about the graph, okay. And this is a table. And the table, in fact, in computer, the data structure is suitably is we are using the matrix. The later we will just talk more about the matrix or the computer like this data structure matrix. And then we can to compute how to compose using the matrix operation, okay. And if you just describe the set, we just use the set operation. But if we just use the graph, we can use the graph the operator, for example, the path search. Okay. So here we just to say if we just using the graph to describe our the relation set, then with the combination just means find the path, whether or not they have existing the path from S element to C element. Okay. And you just using the original one, just like this, like compose RAS. So you should be careful. If it compose RAS, then we can say just from the video, just give the result like write down like this. If you just say like this, S and R, if you just S and R. So maybe you would just look at a glance, you maybe say it is similar, but in fact they are not similar because here we have write down, if you just compose S and R, then we should to write down S is right and R is left, just like this. So here it is that means first we are beginning from S. That means we should beginning from this and to check one by one. Okay, now if you just begin from this, from S, the first element, they have a pair, 1, 0, and now we just find the second part, 0, and to meet whether or not from this, because here S to R, so we just want to find whether or not they are pair. There's a pair, but the first part is beginning at 0, but we didn't find the 0. So it is no way. That means have just have not to meet this 0, just like this. We have mentioned like this. You have reached the B3, but from S set they have no beginning from B3, so have no way to reach this. And similarly, here, that means we have no way from 0 to reach any of the other part. I have no beginning with 0. It's beginning from 1, 1, 2, 3, 1, 2, 3, 3. So have no. Also similarly, I have no. That means these are two elements we have cannot to reach. Okay. Now next, this is from the 3, beginning from the 3. Okay. Beginning from the 3. Beginning from 3, and then the end from the 1. And here we can find the beginning 1 and the beginning 1. So that means we can reach from 3 to 1, and from jump from 1, 1, we can to jump to here. This is 1, okay. And similarly, we can from, if just from this, we can jump to 4. So we can jump to 4, okay. And we didn't find any beginning from 1, okay. And similarly, this also have beginning from 3, okay, beginning from 3, but we are just the end 2, and now we want to find end 2, a beginning 2, and here we find this 2, so we can reach the 3, so the 3, okay, because only we find only one pair just beginning at 2, okay. And the last one is 4, 1, okay, beginning from 4, okay, beginning from 4, but end for 1. And we have mentioned for 1, we have this, we have the 2 elements beginning as 1, so we can reach 1, 4. So this is 1, and we can 4, And now last one should be careful. We are going to check whether or not they have just have the same element, because the set don't permit they have the duplicate the element. And here we didn't find duplicate 1 3 1 3 4 3 3 4 1 4 4. So have no duplicate, so that is okay. So you will find this different order for the composition R and S. They will give us the final different result. So you just compose R and S, then we'll get the. You just